Hello, everyone. Welcome to our talk on the challenges of building application-aware regional disaster recovery in Kubernetes. My name is Veera Deenadhayalan. I'm from IBM Research, and I have with me a co-presenter, Shyam Ranganathan, who is from Red Hat. So here is our agenda for the day. So we are going to quickly go over the regional DR overview, and then talk about DR requirements in Kubernetes, then talk about the present landscape of Kubernetes, what's available, what can you do today, and then a few other considerations to take into account when working in Kubernetes for DR. And then we are also going to present an approach to DR in Kubernetes. And then we're going to talk about things that are evolving in the Kubernetes world that's going to potentially make a life easier to implement DR. Just to point out that our talk covers only the features of base Kubernetes and not about hosted platforms or service providers. So let's jump right into regional DR overview. So every organization has strengths, opportunities, weaknesses, and threats. As part of its risk management, one of the things that an organization needs to deal with is disasters. They need to have a business continuity plan, which includes a prevention plan and a recovery plan for their IT infrastructure. And as part of recovery, they may have a plan to recover from a zone failure, zone being a data center failure, or the failure of an entire region, which could take out multiple availability zones in that region. Now, going from bottom up, the system will have high availability to begin with, but that is not sufficient. You need to build a DR solution on top of it to handle the failure of the entire system. Whereas fault tolerance or high availability deals with subsystem failure, but not the entire system failure. But there seems to be, it appears to be a lot of overlap, but we'll go into the differences in the coming slides. So here is a cluster, Kubernetes cluster, which is going to talk about the goal of DR so that we are on the same page. So consider a Kubernetes cluster here. For example, in the West region, there are 3 control plane nodes and a bunch of worker nodes. So these nodes are basically CPUs, be it virtual machines or bare metal CPUs. And what this cluster has is it has an etcd database, a key value store database. This is where Kubernetes stores its application resources. These are think of it as the YAML files or the JSON files, basically object schemas for various objects that are in the cluster. Things like pod definition, persistent volume definition, service definition, deployment definition, various things, right, which we will touch upon in the coming slides. And then, so that is the cluster state, the app that contains the application resources. In addition, you also have application data, which is the persistent volume data. So this is where the pods read and write data too that are stored inside the cluster. So if you want to protect the cluster, we need to protect what is in the etcd database and in this persistent volumes. Now, in preparation for, if you're going to solve provide regional DR, our clients should come through a global traffic manager, and the normal conditions come to this Western region. But in the event the West region fails, we want to fail over the workload to another region, in this case, East region, which has identical sort of similar control planes and worker nodes, and also has the etcd, the app resources and app PV data that we're running here, so that the clients can start coming to this newly failed over cluster. Of course, if you have to do this, we need to have prepared this cluster either via replication, directly sending it to the other cluster, or sending it to a backup vault to some sort of an external storage outside of this cluster, and then pulling it from that external storage at the time of recovery to restore this cluster. Those are the two options. Now, this is about fail back. Now the workload has failed over and is running here, but if at some point the original cluster recovers, the original region recovers, then we want to fail back the applications and the clients back to this cluster. And to be able to do that, prior to that, we need to resync the data to this original region, or again, go through the backup path, taking it outside of this cluster to a store, some sort of a storage here, and then restoring it here prior to failing back the application to the other side. So now we're going to talk about the ideal DR solution, so that it gives us an introduction again. So here what we have is a timeline, and we spoke about replication or backups. So these green triangles are those points at which this backup or replication is done. Now, in the case of synchronous DR, this event happens for every single IO. In the case of asynchronous replication, this backup happens or replication happens, and then the client IOs are happening on the primary between these two window, multiple IOs are happening, and then again a replication that sends all the changes incrementally or has to make a full copy, however it is, but all these IOs are bundled and then backed up in these intervals. Now, if in this timeline we had a disaster event, what happens? Now, we got to go back to what was the most recent replication or backup event, and then understand that this time window between the most recent replication event and the disaster event, any IO that has happened will be lost, right? That's the data loss time window. And of course, if it is synchronous replication, no data will be lost. So this data loss window is known as the replication point objective. Now, at some point, we recover on the failover cluster. We fail over to another cluster and we do a successful recovery, but that's going to take some time between the disaster event and the successful recovery. During this time window, clients are unable to access the system, and that's called the availability loss time window, or more commonly referred to as the recovery time objective. Now, as an IT administrator, or if you go to the CIO, they would want a zero RPO, which means essentially synchronous replication. And now, whether automatic, in that case, when you're doing zero RPO, automatically you can fail over to the other cluster because no data is lost. But however, clients generally prefer admin triggered fail over to the other cluster, but still automated. It's not automatic, but automated disaster recovery on the other cluster, so that the client accepts the data loss because the RPO is, even if the RPO is zero, they still want to acknowledge whether I do want to move the applications to the other side, because there could be latency incurred to the clients. Now, if you're doing async replication, the RPO is non-zero, and in that case, definitely we want the admin to acknowledge and accept this data loss before failing over to the other cluster. Now, we ideally want this RTO to be as low as possible, and that depends on whether we had the other cluster in standby ready to go, and whether did we have a backup mechanism on elsewhere, and we have to restore it, hydrate the volumes, etc. That affects this time window. And then ideally, to do this failover and failback orchestration, it'll be nice if we can have a single pane of glass, as opposed to logging into one primary cluster and then going to the secondary cluster and doing administrative actions. Now, we spoke earlier about two-region replication, replicating from one region to another region. It's possible to set up replication also across three regions, or three-way replication. Now, in that case, that offers us some choices, right? Now, it's possible that the two replicas are a little bit out of sync because replication is happening asynchronously. In that case, our DR solution should be able to choose the most recent copy of the data, right? The least data loss. That's something that's required. And then if both of them have the same data loss RPO window, then can I I'd like to load balance between these two, right? So that I want to go to the least loaded cluster, failover cluster. And then when I'm failing back, I need to do some coordination for repairing the cluster and then failing over. And also, whatever was applications were running on the failover cluster needs to be brought down because I'm bringing it back to the original cluster. So that requires some coordination. And if there are three-way replica, then we need to fail back to the correct home cluster, right? We need to keep track of what is the preferred cluster. System needs to do that if you're going to help in the automated failback. And then relocate is another use case where we want to relocate an entire application or the entire cluster to a different region. Now we're going to go into the DR requirements, and I invite Shyam to go into that.
Thank you, Veera. So Veera just went through the overview. Let's peel things out a bit and look at Kubernetes and what requirements we have in Kubernetes for disaster recovery. So typically, Kubernetes cluster is divided up into multiple namespaces. Oh, sorry. Before we go there, we're actually splitting this up into three pillars: uh, application resources, application data, and cross-cluster services. Application resources, as Veera referred to, is things stored in etcd, basically resources created for the application to function in a cluster. Application data is where it stores its persistent data. And we'll also look at some cross-cluster services that enable smoother or more reliable disaster recovery. So starting with application resources, typically, Kubernetes, we're going to look at a Kubernetes cluster and how an application is deployed in the Kubernetes cluster and extract requirements out of it saying what needs to be protected. So kube clusters are typically split out into namespaces, and users or groups of users are given access to these namespaces to deploy their applications or containers or runtimes. And so one of the first things that we need to actually protect is the namespace and access to the namespace. That has to be made available across peer clusters during disaster so that applications can be recovered in these namespaces. Now, a user typically deploys an application into a namespace. And in this particular example, we're kind of looking at a pod, keeping it simple, not talking about deployment sets and stateful sets and replicas and all that. A pod is a unit which runs an application. And we've taken an example of a pod which actually stores some data, right? So that comes as a resource, a persistent volume claim resource, which is the PVC, which is what the user creates saying, I need a persistent volume. And the system satisfies that need by creating a persistent volume object based on whatever storage plugins are configured within this Kubernetes cluster. So as you note, the persistent volume claims a namespace resource, whereas the persistent volume is a cluster scoped resource. So that we're already transitioning namespaces and going beyond namespaces. And also the persistent volume is a dynamically created resource. So again, these are not necessarily created by the user, but because the user desired something, something else is born. And these are the objects that need to be preserved when we go across clusters during disaster recovery. Pods usually have services. That's how other applications within the cluster reach out to use the pods services. But applications do not exist in isolation. Typically, an application or a pod provides a service, and the dependent applications accessing that particular service via the service endpoint, or it could be a client outside the cluster or users outside the cluster accessing the service via an ingress endpoint for which allows inbound traffic to the pod. So again, we're looking at services, or we're looking at resources which are not necessarily restricted to a single pod, but other pods, other dependent applications that need to be grouped, and ingress or inbound rules to allow application access. Now, applications also could create custom resources. What are custom resources? Kubernetes API can be extended using custom resource definitions, CRDs as such, to provide enhanced or added functionality. For example, you do not want to create a raw DB container, database management container, and manage it. Whereas there is a DB manager, which would ensure this DB container is upgraded correctly, does blue-green deployment or whatnot when it's getting upgraded, so on and so forth. So an application may end up using such custom resources. And these custom resources are API extensions, which again becomes a cluster scoped object or an API resource in that sense. And the actual operator that reconciles requests, custom resource requests of this kind are completely running in a different namespace. So again, during disaster recovery, you not only need to recover the application, what's in that primary namespace, but you also need to have an equivalent configuration on the alternate cluster, which can handle these extensions as well. So this was about application resources. So if you take a look at data, we've made it very simple. Application data needs to be protected. Veera has talked about backup. Veera has talked about replication. We're kind of more keen on storage replication and how to make that happen, and we'll see why. But application data needs to be replicated across the tier clusters that are in a DR relationship. And finally, we look at certain cross-cluster services. Veera briefly mentioned GTM, the Global Traffic Manager, which needs to be rerouted so that it points to the ingress endpoint, or it points to the endpoint where the application is actually running, rather than when a disaster happens, rather than point to an arbitrary cluster where the application is no longer running. So that needs to be configured, and that's looked at as a cross-cluster service. Similarly, to detect that a cluster is down, up, available, you need some form of health monitoring. And these are better served outside of the cluster peers, especially in two-region cases where you really need a third leg or an arbiter so that you can form a proper. The monitoring is done by an external entity and not within these two clusters. That forms another cross-cluster service as a health monitor that can look at the cluster health and start the DR operations going further. Finally, DR orchestration is another service that is best served as a cross-cluster service. Failover, we just saw that failover is fine. You just restore the data and then you restore the applications, you're done. But when we look at failback, there is enough coordination that needs to happen between the cluster where the app is running to the preferred cluster where the app needs to run. So you need to stop the app, you need to quiet the storage, sync the storage. So there's quite a bit of orchestration that happens during failback. Even for failover, actually, there is some orchestration that needs to be done. And this is again served better as a cross-cluster service rather than as an in-cluster service. So in summary, what we have across these three pillars is application resources. We need namespaced objects, equivalent cluster configuration, custom extensions provided across the peer clusters. Dependent applications need to be grouped. We need application data, and we need a series of cross-cluster services that can help us orchestrate DR, detect availability, and such. Moving back to Veera, let's talk about the Kubernetes landscape.
Yeah, thank you, Shyam. So we want to quickly go over the high availability features in Kubernetes, just to clarify how it helps in the process, right? So Kubernetes has several high availability features. So in this, if you see, the worker nodes are separated from control plane nodes, so that any problems that are happening in the worker node does not affect the control plane node. So that separation is part of the architecture itself. And in this example, the etcd nodes or etcd service is running in the control plane nodes. However, if you want more resiliency, you could also take the etcd and run it outside as an external cluster. And as far as the communication between worker nodes and control plane nodes, the worker nodes go via a load balancer to reach the control plane node so that they don't overload a particular control plane node. Given all these high availability features, just wanted to point out that these are dealing with node failures and node overloads and that sort of a thing. But in the case of a regional DR, it is about the loss of an entire cluster. So HA is not sufficient. It's not going to replace the regional DR need. Now, we spoke about backup and replication, but we're going to go into a little bit more detail here. So in Kubernetes, you can do these two methods, right? Backup-based or replication-based. If you do backup-based, what happens is the application resources and PV data or stored in a backup vault. However, the RPO and RTO are coarse because currently, you need to, if you're going to restore it to the failover cluster, you need to take the entire data that is stored in the vault and bring it to this Kubernetes cluster, the failover cluster. That's going to involve some time and definitely has an increased RTO. And note that just doing an HCD backup is not sufficient because the HCD backup only covers the application resources, does not contain the application data or the PV data. Whereas if you do storage system replication, then this is using leveraging the storage system layers replication ability. And what you need to make sure is, if you do that, does that solution also take care of application resources that are above the storage layer, right? That's something that you need to make sure that comes with the solution. That the solution offers better RTO in terms of PV data because the PV data is ready on the DR peer cluster side, as opposed to backup. You need to hydrate it from the backup. That problem is not there. Now, the above approaches may not fully address your DR requirements, and that's where you need to go into what are our DR requirements and what are addressed here, right? So here, what we are saying is, we basically saying that some of the requirements are met, but basically in terms of cross-cluster services, definitely are not met in the solution of either backup or just replication between two peer sites. Then in addition, the thing that we mentioned about the, if you do storage replication, does it include the application resources or not? That needs to come as a custom solution, and there is no generic solution that applies to all Kubernetes environments.